Okay, so let's have a look. So we start with our acid chloride, which is our very reactive species. So therefore we can take our weaker nucleophile and we can just react it straight away. We break the carbon-oxygen double bond. It's going to give us our O- here. It's going to give us our Cl. And it's going to give us our ethanol added. We can then reform the carbonyl bond and we can get that chlorine to leave because it's a very, very strong leaving group. That gives us our ester, although we still have this positive charge to deal with. So once we've deprotonated that, we are going to get our ethyl ester, and that was molecule A. So then once you know that you've got an ester, so if we take our new ester that we've just formed and we're going to put it into a different reaction mixture, so we're going to take this and we're going to put it in the presence of some acid. Therefore the first thing we're going to do is just to protonate that oxygen. So we end up with this protonated activated oxygen. We've then got our H2O. Let's draw that as H2O. We've got the lone pair of electrons on the oxygen that are going to attack our activated carbonyl. We break the carbon-oxygen double bond. We then end up with our tetrahedral intermediate. Okay, we then do our proton transfer. That's going to be, again, it's all in equilibrium, so that proton is going to be transferring between all of these oxygens, but at some point we're going to end up in the equilibrium, we're going to end up in this position, and at this point we can use one of the hydroxyl groups to reform the carbonyl bond, and we can lose that ethanol as our leaving group. It's going to end up giving us our carboxylic acid, which once we have deprotonated gives us the product that we were looking for. So we've looked at oxygen as a nucleophile, we've looked at reacting alcohols, and that's where we get things like transesterification, and then we've looked at hydrolysis. So one of the ones to now look at would be the idea of a nitrogen as a nucleophile. So the idea of either making amides instead of making esters to start with. So if we react amines with carboxylic acids, we can try to get amides. But these reactions are complicated by the fact that the amine itself is basic, and so it's competing with it being acting as a nucleophile. So the idea is that if you put these two things together, you've got a carboxylic acid and you've got an amine which acts as a base. What's likely to happen is these are likely to form some kind of ammonium salt, and then you have to actually put in a huge amount of heat, remove water from the reaction mixture to finally get your amide. So it's a really quite complicated way of trying to make an amide. What we ultimately want to do is use one of those more reactive carboxylic acid derivatives. So we would take something like the acid halide, the acyl halides or anhydrides, to do that reaction. So if we take an acid chloride again, okay, and we can take our amine. Again, the acid chlorides are very reactive, so we don't need to worry about this kind of activating them in any way. We get our tetrahedral intermediate. We have that positively charged nitrogen. At this point, it's just worth showing that we have something which is basic. So we have our NH2R. This can actually pick up that proton to help with the deactivation we can deprotonate that nitrogen. So we've now just got our NR2 group there, we've lost that proton, and then we can reform the carbon oxygen double bond and lose chlorine as a leaving group. And there we have our amide at the end of it. We can do exactly the same thing with the anhydride example. So same mechanism. Okay, you take your amine, you react it with one of those carbonyl carbons. That gives you your classic tetrahedral species. Where we've added our amine, again recognizing that what we have here is a base that can help deprotonate. Okay, so we end up with our adding our nitrogen, and then again at this point we reform the carbonyl bond, the carbon oxygen double bond, and we get this carb anion as a leaving group. And what that gives us at the end is an amide plus this very stable anion. So that would be the really straightforward way of doing this. As I said, we can use esters to try and make amides from. So we looked at the carboxylic acid, that was a little bit complicated, but the esters can work. So again, if we take an example of our ester, we'll use an ethyl ester, and we'll use a simple amine. We can again do that reaction with the amine onto the ester carbonyl group, break the carbon oxygen double bond, and get to our classic tetrahedral. That's because that ammonia at the start is quite a good nucleophile. Again, at this point we can deprotonate, so we can take a proton from here, okay, and then we get to a point where we have a choice again. So if we just draw that molecule a second time, we can have a look at what would happen with this choice. And it's very similar to the examples we did with the aldehydes and ketones. Do we use the O-ethyl group as a leaving group, or do we use the NH2 group as a leaving group? So if we do what we want to happen, which is reform the carbon oxygen double bond and kick out the O-ethyl group, what we end up with is the product we want, which is our amide, plus O-ethyl minus. If we go the other way, which is effectively reversing what we did before, so doing the reverse reaction, reform the carbon oxygen double bond and lose the nitrogen, we're going to end up with the ester that we started with, and we're going to have this NH2 minus. Now, we can look at that and understand that, you know, oxygen is more electronegative than nitrogen, and therefore the oxygen up here is likely to be far happier having that negative charge than the nitrogen down here is. When you look into more detail, there's lots of information about using pKa values to determine this, to be able to say, well, which one is the better acid or which one's better conjugate base. But ultimately it comes down to the oxygen is going to be more stable as an anion in its own right, because the oxygen is happy to have more electron density. It doesn't cause as much problem. The nitrogen is less happy to have that, and so the nitrogen wouldn't really want to exist in this NH2- form. So in reality, this reaction doesn't occur, that reverse reaction. Once you get to this kind of position with the tetrahedral intermediate, we are really going to push the reaction towards forming the amide. Okay, so the other thing just to point out is that at this point here, we need to be able to remove that proton. So if you were to take an example of a nitrogen nucleophile where you had NR3, for example, did this reaction, break the carbon-oxygen double bond, you would end up in a position where you had your nitrogen and you had your 3 R groups positively charged. You don't have a proton there to deprotonate to help push the reaction forward to the amide product. So this tertiary amides cannot act as a nucleophile in this particular reaction mechanism. Okay, so another chance for you to try and see if you can follow what we've done there. So this time we're going to take the nice, reasonably simple anhydride example, and we're going to react that with an amine. So your nitrogen lone pair in the amine is going to act as your nucleophile, and you're going to react it with the anhydride.